Hey y'all, this is the second video on improper integrals here. We did these three. We talked about that as much as I want to talk about it for now. Now we're going to work into these two here and then hopefully get this one in as well. Remember, these two are improper integrals because if I try to plug this 0 into that function right there, I get a 1 over 0, which is something that we can't do in math. I have to use limits to talk about having a 1 over 0. After you recognize that this is an improper integral, the process is pretty similar to what we talked about in the previous 2 or 3 examples. So what we need to do is use limit notation. Oh, I should show a graph of this one. This is the same y equals 1 over x graph or x squared graph that we used above. Notice this is x equals 1. So previously, we said that this green area over here, if I were to go underneath the curve all the way out to infinity, that was equal to 1. Notice with this one, I'm going from 0 to 1, because those are the bounds here. So just like the other one had a function that asymptotically here approached the x-axis, here I've got a function that is asymptotically approaching the y-axis. As we go closer and closer and closer to 0, this thing goes closer and closer and closer to infinity. So here we are calculating this area right there. And you should see that the blue area, that's definitely going to be bigger than the green area. So in this one, there's a chance that this thing will diverge. And again, it all depends on this power right here, and I think you might be piecing that together a little bit. So let's do the problem. This is the limit as, remember, I'm going to take a goes to infinity, not infinity, sorry, a goes to 0 of the integral from a to 1 of 1 over x squared dx. And now it's legitimately like workable. Carry my limit notation as a goes to 0. All right, that gives me negative 1 over x evaluated from a to 1, which is the limit as a goes to 0 of open bracket. I got a negative 1 over 1. That's this evaluated at the first bound, minus a negative 1 over a. And I'll simplify this a little bit so that it's a little bit easier to see. You might already see that this one diverges. If I write this and take care of all the negatives, this is the limit as a goes to 0 of, I actually have a positive 1 over a. It's the same move we did in the previous one, minus 1, close bracket. Is that right? It's right. So look, what do I get here? I get a problem. If I take the limit as a goes to 0 and this a is in the denominator of that fraction, then this fraction goes to infinity. So what do I write as my answer? I write diverges or divergent. Either one is totally fine. Why is that? Because when I try to evaluate this integral between the two bounds, I get something that goes to infinity. So that's interesting. 1 over x squared, if I integrate it from 1 to infinity, it gives me 1. But if I take it just from 0 to 1, then it gives me something that is infinitely uncountable. Okay, let's do the next one. So here we go. Integral from 0 to 1 over root x dx. Remember, this is 1. This is the area that we calculated before in example, I don't know, was it 2? Up here, I don't think I put a 2 there, but if we go up here, that was this one right here. Remember, that one was divergent, and that was this from here out to there. Notice it didn't hug the axis as much as the other one did. So that green one is divergent, but the one that I'm looking for now is from here to here. So notice it hugs that y-axis much faster than this green portion here hugs the x-axis. So I feel like there's a chance here that this one's going to converge. So let's do the calculations. It's the limit as a goes to 0 of the integral from a to 1 of 1 over root x dx. So that is the limit, don't forget your limit notation, as a goes to 0 of, all right, I got 2 root x evaluated from a to 1. And notice in this spot here, like I can't think about 0 being in here and numerically quantify it. It just goes to infinity. But look here, now that because of power rule, bumping this power up by 1 unit when I integrate it, now I've got 2 root x evaluated from a to 1 when a goes to 0. And that's one, there's no problem there. I can plug it in. And that's what we do with limits. When we just plug them in. So that is equal to 2 root 1 is the upper bound. 1 minus 2 root 0. I could put an intermediate step here, but I think you should be able to see this, right? That's just this evaluated at those 2 bounds. And then that gives me, all right, 2 times root 1 is 2. 2 times root 0 is 0. 2 minus 0, so I get 2. So this one, the previous one, it diverged. This one is a number right here. So that's this chunk of area right here and then up there. It's actually sort of interesting to me here because look at this. If I take this area right there, that's clearly a part of the blue chunk, and that thing is 1 unit by 1 unit. So that is one of those 2 units of area. The rest of the area up here, if I go all the way out to infinity, under this thing, or the left of this thing, is the same as the area in this little box right here, because 1 plus 1 is, everyone, 2. Let's explore this a little bit on Desmos. The red one is 1 over x squared. So inner area from here out to infinity, remember that was 1. Area from 0 to 1 under the red, remember that diverged. Okay, now if I look at the blue, which is 1 over root x, if I go integral from 1 to infinity, that one diverges. And then this one right here, at the blue, if I go from 0 to 1, that area is 2. So I'm going to turn this on right now. This purple graph is y equals 1 over x to the n, where I've got a slider here for n. So it will animate this with different values of n. So I want to hit play. You can see it going through. As n gets bigger, this purple graph hugs the x-axis more and hugs the y-axis less. And then that statement will be flipped as n gets closer to 0. Watch, as n gets closer to 0, it'll get away from the x-axis and go closer to the y-axis. And there's some symmetry here, and you might see it. So boom, I almost got it, but I almost got it at that 2, right? So 2 would be boop, 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 2. Notice that lands on this red graph. So the question that I posed with the 1 over n is basically asking, when will this purple graph, or what value of n does this purple graph hug the x-axis enough that the area becomes unbounded and is a number, as opposed to being, that the area becomes bounded and is a number, as opposed to being unbounded and divergent going to infinity. The last example is the integral from 0 to infinity of x times e to the negative x dx. Notice x to the e to the negative x is an exponential decay. As x gets bigger, this thing gets smaller and smaller very quickly. And x is something that grows, but not as fast as the exponential decay. So what I've got here is a function where I'm multiplying something that gets bigger by something that gets smaller, but smaller very quickly. So the question is, does this thing converge or does it diverge as x goes out, or as the bounds go out to infinity? And just so you can visualize it, I've got the 2 graphs that we worked off of initially with the green x e to the negative x on here. So you can see, remember, I'm going to do all of these from 1, well, I did the red and the blue from 1 to infinity, right? It's clear that this is a finite area right here. So really the question is, what happens as we go out to infinity here? To me, it looks like, all right, it looks pretty close to this red one, but it's definitely bigger than the red one there. And I don't know if that bigger spot right there is enough. My guess is going to be that it converges. It's definitely smaller than the blue graph. Remember the blue graph? That was the root x, the 1 over root x, and that thing diverged. So it could diverge, it could converge. We need to calculate to figure it out. So we have to start with our limit notation. This is the limit as b goes to infinity. I don't have to use a 0 for with the limit the way I did with these here, because I can plug in 0 to these and I don't get some undefined piece. But I get the limit as b goes to infinity of the integral from 0 to b of x e to the negative x dx. And you should say, oh, I got to use integration by parts for this one. So I got to do a dir column and an int column. Dir is x, 1, and 0. Int is e to the negative x. Negative e to the negative x, some chain rule there. And then, again, a positive e to the negative x. Diagonally, plus minus. So this gives me the limit, don't drop your limit notation, as b goes to infinity of all right, this will be, I'm no longer going to draw an integral sign. That's what I almost did there. I'm going to evaluate it, which is this stuff here. So I get a negative x e to the negative x minus e to the negative x, close, evaluated from 0 to b. Now, in order to make this a little bit easier to see, I'm going to rewrite these e to the negative x's as fractions. So that is the limit as b goes to infinity of negative x over e to the x minus 1 over e to the x. Close, evaluated from 0 to b. Now, this is, I'm going to go ahead and write it as an evaluated piece because I think it'll be easier to see. It is the limit as b goes to infinity of, all right, I got negative b over e to the b minus 1 over e to the b minus, open parentheses, this thing evaluated at zeros. So notice this is convenient. I get a 0 in the top, so it's 0. And then minus 1 over e to the 0 is going to give me 1. Close and bracket. So here's the deal. This stuff's easy. This 1 over b, limit as e goes, or 1 over e to the b, as b goes to, that is an exponential growth in the denominator of a fraction. That's going to go to 0. You should see that. This goes to 0. Next one, I've got negative b over e to the b. In the top, actually you can ignore the negative. In the top, we've got a linear growth. In the bottom, we have an exponential decay. You could, if you wanted, use Hopital's rule with this one because it does go to infinity over infinity. You could hop it and get an answer, but I think it's easier to logically, and this is acceptable on the AP test, to say, all right, in your head, all right, I got a linear growth versus an exponential growth. What's going to win? The exponential growth. And when the denominator wins, just like this one over here, it goes to 0. So this gives me, I will do a bracket to stay consistent, 0, a negative 0. I said ignore the negatives, it's carrying, but it doesn't matter. Minus 0, minus 0, minus 1, close bracket. And that, all right, these are all zeros, a double negative on that 1. I get a positive 1. So what that tells me is that the area under that curve is 1. And back to Desmos, that tells me that the area from 0 out to infinity under this green curve is the same as the integral from 1 to infinity under the red curve. So this is improper integrals. They're integrals that involve infinity. Hopefully they're making sense, and they will become super important as we get into what we are doing next in calculus.